In this lecture, we're going to continue looking at rotational motion. So in particular, we're going to be looking at torques, Newton's second law, kinetic energy, and the conservation of angular momentum. And like with the last lecture, this will be much easier if you keep on thinking about the analogies between rotational motion and translational motion. So the textbook reference for this lecture are your Halliday, Resnick and Walker textbook, sections 10.6, 10.7, 10.8 and chapter 11. So first of all, a quick recap of the most important ideas in the last lecture. In the last lecture, we saw that translational quantities have rotational analogies. So an object moving around a circle can have radial and tangential acceleration. We've already looked at the radial acceleration when we were considering uniform circular motion, but if an object is speeding up, then it can also have a tangential acceleration, which can be calculated using r alpha, where alpha is the angular acceleration. We saw that the moment of inertia of a body is given by moment of inertia is equal to the sum over I of mi times ri squared, and this is for discrete objects. Or if we have a continuous body, we can calculate the moment of inertia as the integral of r squared dm. And we saw some examples of how to perform these calculations. We saw for a sphere, the moment of inertia is given by 2/5 mr squared. Okay, now you actually already know quite a lot about torque. Consider these doors here with the door handle and hinges marked on. Now, which door is going to be easiest to open? Okay, so hopefully it's fairly clear to you that it's easier to open the door when the handle is a long way from the hinges than when the handle is right next to the hinges. So this door here is the easiest one to open. And how do you open it? Well, you open it by applying a force on this door handle, pulling it in a direction which is perpendicular to the door. Okay, so this force that you're applying is actually a torque, a turning force. And the equation for turning force is given by tau, which is our symbol for torque, is equal to r cross F. Now r, this is the vector pointing from the pivot point. So with our door, it's pivoted about these hinges to the place where the force is applied. So with our door, we're applying the force on the handle. So r is this vector here. Now the force, that is the applied force. And for the torque to be maximum, it needs to be perpendicular to this r vector here, which is why we pull the door perpendicular to the door itself. So r points from the pivot to the place the force is applied. So as we know, because this is a cross product, we can calculate it as a sine theta. So we can say, or sine phi as it's written here. So we can say, well, tau is equal to rf sine phi, where phi is the angle between r and f. Now, the units are written as Newton meters, which you may realize is the same as joules, but we never write a torque as joules, as the meters vector and the force vector, the Newton's vector, are perpendicular to each other. So it doesn't really make sense to combine them into something called joules. So this isn't an energy, so we just leave it as Newton meters. So here's a problem for you to try. The image below shows the overhead view of a meter stick. The pivot point is the dot, so that's here, 20 centimeters from the left-hand end. All 5 forces on the stick are horizontal and have the same magnitude. Rank the forces according to the magnitude of the torque they produce, greatest first. So with this problem, we've got our rod here. It's pivoted about this point, 20 centimeters from the end. We've got F1 here, F2 is here, then this point here is also 20 centimeters. From the pivot point, we've got force F3 and force F4, and then we've got force F5 at the end here. And we know that the torque is given by R cross F. And in this case, all these forces have the same magnitude. So we can write this as RF sine phi, where phi is the angle between R and F. Okay, so torque 1 is going to be equal to the 20 centimeters times the magnitude of the force. So R1 goes this way from the pivot point to where the force is. Force 1 is at 90 degrees to that. So this is going to be equal to RF. Now torque 2, there is no distance between where the force is applied and the pivot point. So R2 is actually 0. So torque 2 is going to be 0. This doesn't apply any torque. Torque 3, again it's 20 centimeters, so it'll be R, where R is 20 centimeters times F. And like with force 1, the angle between R and F is 90 degrees. With F4, you can see that this angle is greater than 90 degrees. So sine phi is actually smaller for force 4. So torque 4 is going to be less than torque 1, which will be equal to torque 3. And torque 2 is 0. Now torque 5 is also 0 because the radial vector in this case is in this direction, the force is in this direction, and so when we have the radius and the force parallel, the cross product's 0. So torque 5 is also 0. So we can say torque 1 is equal to torque 3. They are greater than torque 4, and that's greater than torque 2, which is equal to torque 5, which is equal to 0. So now we're going to look at Newton's second law for rotation. We've spent quite a lot of time looking at Newton's second law for the translational case, so we're all quite comfortable using that the net force is equal to the sum of the forces acting, which is equal to the mass times the acceleration. Now for the rotational case, there's an analogous equation. We've got that the net torque is equal to the sum of all the torques acting, and this is equal to the moment of inertia times alpha, the angular acceleration. So let's consider the simplest case and see if we can show this equation. So imagine that we have a massless rod of length r and we place a mass m, a point-like mass, on the end of it, and then we apply some force to that mass. Now we'll let our rod have an angle theta with the horizontal, and we'll let the force have an angle phi with the radius, the length of the rod, as shown in the figure. Now if we want to calculate the torque that this force causes, we can use that the torque is equal to R cross F, which is equal to RF sine phi. Phi here is the angle between the radius and the force, just like we've shown in the diagram. So this is actually equal to R times the tangential component of the force, as we can break that force into a radial component and a tangential component. So the tangential component of the force is equal to the mass times the tangential component of the acceleration. That's just an application of Newton's second law for the translational case. And we have seen that the tangential acceleration is given by alpha times r, where alpha is the angular acceleration. So let's put all of these together now. We've got that our torque is equal to the radius times the tangential force. So the torque is equal to the radius times m times the tangential acceleration. So the torque is equal to the radius times m times alpha times r. Or we can rearrange that to write it as mr squared alpha. Now for the object we've just described, a massless rod with a mass m on the end, a distance r away, the moment of inertia is just given by mr squared. So you can see in this case the torque is equal to I alpha. But is this generalizable, or have we just shown it for the simplest case? Well, we can actually extrapolate this for all cases, because whenever we're considering a continuous body, we just break it up into lots of little components and add all those components together. So by showing it for one small component, we can actually extrapolate this to whole continuous bodies. So the generalizable formula is that the net torque is equal to I times alpha. So let's have a bit of a look now at a physical example where we can actually make use of this equation. So the question is, consider the Atwood machine pictured with M1 is equal to 1.0 kilograms, M2 is equal to 2.0 kilograms, capital M is equal to 1.0 kilograms, R is equal to 0.10 meters. Calculate the acceleration A of mass M1. Okay, so this question is a little bit different to previous ones where we have ignored the mass of the disk. We now know enough about rotation to account for the moment of inertia of this disk in our calculations. Okay, so in this one, we start with the normal way. We'll use Newton's second law to write down the forces on all of the three bodies in the system. So on mass M1, mass M2, and also on the pulley. So on M1, we've got a tension pulling it up. Because of the pulley, there is a different tension on either side. So we've got tension 1 over here and tension 2 here. So using Newton's law with mass M1, we can say M1A is equal to the net force on M1, and that's caused by the tension force. Now, because M2 is heavier than M1, we can safely assume that it is going to accelerate this way. So we can say the tension force is pulling it up, and then we've got the weight force pulling it down. Those are the only two forces acting on this mass. On mass M2, we've got the weight of M2 pulling it down and the tension pulling it up. So we've got M2G minus T2. Okay, and now we've got to consider our pulley. We've got two forces acting on the pulley. We've got T1 and we've got T2. And these are going to act to give it torques. So we can write I alpha is equal to the torque due to this one, which is given by R times T2 because it's acting at 90 degrees, it's pulled along the radius, minus RT1, as these forces are acting in opposite directions, so they'll create torques in opposite directions. Now we're going to want to simplify this expression a little bit. So there's a number of things that we can do. First of all, we know that the moment of inertia of a disk is given by a half mr squared. So we can substitute that in for I. We also know that the acceleration is related to the angular acceleration through the acceleration is equal to r alpha. So this tells us that alpha is equal to the acceleration over the radius. So we can substitute both of these into this expression here. So we've got a half mr squared times a over r is equal to r T2 minus T1. Okay, now what we can do is cancel this r with one of these r's and the r on this side with the r on this side, which gives us a half ma is equal to T2 minus T1. So let's write that down here. We've got a half ma is equal to T2 minus T1. Now what we have is three equations, 1, 2, 3, that we can solve simultaneously. So we can do 1 plus 2 plus 3, and this gives us m1a plus m2a plus a half ma is equal to T1 minus m1g plus m2g minus T2 plus T2 minus T1. So now you can see the really nice thing is that this tension cancels this tension cancels this tension, and the acceleration is common across all of these terms. So we can rearrange this and say, well, A times m1 plus m2 plus a half m is equal to m2g minus m1g. And then we can rearrange it to get our acceleration. Our acceleration is equal to m2 minus m1, let's pull g out as a common factor, over m1 plus m2 plus a half m. And now these are all things that we have, so we can substitute in for our system here and solve this. So we've got 2 kilograms minus 1 kilogram times g, which is 9.8, divided by 1 plus 2 plus a half times 1. And then we can solve this on the calculator and we get 2.8 meters per second. So this is the acceleration of mass m1, and so we can say m1 has an acceleration of 2.8 meters per second upwards. We're now going to consider work and kinetic energy for the rotational case. So we've considered this for the translational case before. We've seen the work kinetic energy theorem, which tells us that when we do work on a body, we change its kinetic energy. So the work done on a body is equal to the final kinetic energy minus the initial kinetic energy, and this holds as long as we have no non-conservative forces doing work. We've seen that we can calculate the work in this case using the integral of f dot dx, where the limits on the integral are from the initial displacement to the final displacement. Now, to start an object rotating, we also need to do work on it. For the rotational case, we can calculate the work done on the object as the integral of the torque d theta, where the limits on the integral are from the initial angle, theta initial, to the final angle, theta final. We also end up with an analogous expression for the kinetic energy of a body. The rotational kinetic energy is given by a half I omega squared. So let's have a look at our simplest case now and show that the kinetic energy is given by this expression. So we're now considering the case with a massless rod with length r with a point mass of mass m on the end. We'll let it rotate, and the mass is traveling around its circular path with some speed v. If we want to calculate the kinetic energy when the mass is moving with the speed v, we know that we can just use our kinetic energy formula, that the kinetic energy is equal to a half mv squared. Now in this case, because it's moving around the circle, the speed, the velocity, is given by omega r. So we can substitute that into our equation in place of v. So we've now got that our kinetic energy is equal to a half m and then omega r all squared. Now we can rearrange this expression to write this is equal to a half m r squared omega squared. But as we've discussed with our moment of inertia, the moment of inertia of a point mass is given by mr squared. So we can replace that with I. So our kinetic energy is now written as half I omega squared. Now this is just for the simplest case, but we can extrapolate from this case to all other cases, as when we consider a continuous body, we just break it up into lots of little point masses and then we just sum them all together. So the same thing applies here, and we have effectively shown that for any continuous object, the amount of kinetic energy is given by a half I omega squared. We're now going to be considering rolling objects. So let's start by actually watching this cylinder roll.
So as you can see, I've put a red dot on the outside of the cylinder and a green dot on the center of mass of the cylinder. So as it rolled, the red dot traced out a fairly complex path. This path is actually known as a cycloid, and you may have noticed that the dot was moving faster at the top of its motion than down the bottom. On the other hand, the green dot traveled with a fairly constant speed along the table. So how do we describe this motion? Well, it helps to consider the translational motion and the rotational motion separately. So the translational motion tells us how the center of mass of this object is moving through space. So the speed of the center of mass of a round object is given by V of the center of mass is equal to omega r, where omega is the angular speed of the object. So we saw this equation before when we were looking at circular motion, and that's no coincidence. If we think about how far this disk travels in one period, well, the distance it travels is one circumference like this, which is given by 2 pi r. So it goes through 2 pi radians in that period, and the angular speed is just 2 pi divided by the period. Now, as it translates, it's also got translational kinetic energy. So the amount of translational kinetic energy is given by a half mv squared, where the v there is referring to the velocity of the center of mass. Now, as well as that translational motion, we've also got a rotational motion about its center of mass. So this rotational motion is caused by the torque, which comes from the frictional force acting at the radius of the object. So the rotational motion also has an associated kinetic energy. So the kinetic energy of the rotational motion is given by a half I omega squared. For a disk like this one, the I is given by a half mr squared, but this holds for any shaped object which could have a different moment of inertia. So let's now have a little think about some objects rolling down an inclined plane. Okay, now we've got an inclined plane set up, and I've got two objects that in a minute I am going to roll down the plane. But before I do that, we're going to do a little bit of a predict, observe, explain activity. So these objects are almost the same, except that the masses here, these two bars, are much closer to the center of this cylinder than on this cylinder. So I want you to have a think, if these two cylinders raced down the plane from the same height, which one is going to get to the end first? Okay, ready, set, go. So, as you saw, the object with the mass closer to the center got to the end of the plane first. So, can you now write down why you think that occurred? So the object with the masses closer to the center got to the end of the plane first because it has a lower moment of inertia. So we know this because the formula for the moment of inertia is given by I is equal to r squared dm. So when dm is at a smaller radius closer to the center, we end up with a smaller value for I. Now at the start, both these two cylinders had the same gravitational potential energy. They were at the same height above the end of my ramp. As they rolled down, that gravitational potential energy is converted into kinetic energy. But as we've discussed, there's two types of kinetic energy. We've got the translational kinetic energy, which is making it move along and which makes one of them get to the end faster than the other, and also the rotational kinetic energy. Now, when more energy goes into the rotational kinetic energy, it means that there's less energy going into the translational kinetic energy. So this object with a higher moment of inertia required more rotational kinetic energy. Its a half I omega squared term was bigger, which meant that there was less energy going into the translational kinetic energy, which meant that it was getting to the end of the ramp after this one with a smaller moment of inertia. Let's have a bit of a look at a worked example now where we'll solve a problem for something rolling down an inclined plane.
Okay, so here's an example problem. A cylinder with a mass m and radius r is released from a height h on an inclined plane. Okay, so let's sketch a little diagram. Here's our inclined plane. It's released from a height h here. So this is initial, and down here we've got the final. So we'll assume it's released from rest. And we're asked, what is the speed of the cylinder at the bottom of the plane? So we can once again use our energy conservation because there's no non-conservative forces doing work in this case. It's rolling down the plane, so there is friction, but the friction's not actually doing work because it's not sliding down the plane. So we have that the initial potential energy plus the initial kinetic energy is equal to the final potential energy plus the final kinetic energy. Now the initial kinetic energy, if it starts from rest, is 0 as it's not moving. So this is 0. And at the bottom of the slope, the height is 0, so it's got 0 potential energy. So we can say, well, the initial potential energy, which is mgh, is equal to the final kinetic energy. Now, because it's rolling, it's got two types of kinetic energy. This has got rotational kinetic energy plus the translational kinetic energy. So we've seen that rotational kinetic energy is given by the formula a half I omega squared, and the translational kinetic energy is given by a half mv squared. And because this is a cylinder, we know that I is equal to a half mr squared. So we can substitute this in. We've got a half times a half mr squared. Now omega, it's useful to relate omega and v because we've got a v here. So we know that v is equal to omega r. So we can write omega is equal to v on r. So let's replace this omega squared here with v over r squared. And then we've got plus a half mv squared. So this is equal to a half times a half, which is a quarter, mr squared times v squared on r squared. So those r squareds will cancel out, and then we've got plus a half mv squared. So we can write this as a quarter mv squared plus a half mv squared, which is equal to 3/4 mv squared. So we've got mgh is equal to 3/4 mv squared, and we're trying to get an expression for the speed. So let's cancel out these m's, and then we can say, well, v squared is equal to 4/3 gh, which tells us that the speed is equal to the square root of 4/3 gh. So that's how we can calculate the speed of the cylinder at the bottom of the inclined plane.
The final rotational quantity that we're going to consider is angular momentum. So angular momentum, as its name suggests, is the rotational analogy of momentum in the translational case. So angular momentum is represented by the symbol capital L. Now we saw in the translational case that we could write Newton's second law, F is equal to ma, where a is the rate of change of the velocity, so we can write this is equal to m dv dt. And then as long as the mass of the body isn't changing, we can write this as dmv dt, and mv was just our momentum p, so this is equal to dp dt. Now in the angular case, we have an exactly analogous equation. We've got that the Newton's second law can be written as torque is equal to I alpha, where I is the moment of inertia. So this is equal to I d omega dt, which is equal to d I omega dt, as long as I isn't changing. So I wouldn't be changing if the mass wasn't moving about the body, so we weren't adding extra mass or moving the mass about in the body. And this is equal to dl dt. So from this we can see that L, the angular momentum, is given by I omega, where I is the moment of inertia and omega is the angular speed. So this is exactly analogous to our equation P equals mv, where L and P are equivalent, I, the moment of inertia, is equivalent to the mass, and omega, the angular speed, is equivalent to v, the speed of the body. So let's have a go at a problem using this now.
Okay, so in this example, we have a disc here, a hoop, and a sphere, which all have the same mass and outer radius, and are all initially stationary. They are free to spin about their central axis. The same force, F, acts on each of the objects for the same length of time, t. And from greatest to smallest, rank the objects according to their A, angular momentum about their central axis, and B, angular speed. So in the figure, you can see where the force is being applied. So let's solve this now. So in this problem, we've got a disc, we've got a hoop, and we've got a sphere. And they've all got the same radius, so R, 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 and they've all got the same mass. And they're all acted upon by the same force, F. So here's F. And in the first part, we're asked to rank these in order of their angular momentum. So this force here acts for the same amount of time, t. So in order to consider their angular momentum, let's look at the equation. The torque is equal to dl dt. Now the torque applied on each of these shapes, torque is equal to R cross F. For all of these, the force is applied perpendicular to the radius, and so this is just equal to Rf. So they all have the same torque acting on them, given by Rf. So we can write this as Rf dt is equal to dl. They're all starting from rest. The force acts for t seconds, so they start from rest, so L is initially 0 and it's going up to some final L. So integrating this, we've got Rft, and on this side we've got L. With the zeros, those both give -0 on each side. So we've got the angular momentum, L is equal to Rft. Now R, F, and T all have exactly the same value for each of our shapes, so this tells us that the angular momentum is the same for all of them. Okay, now in the second part, we were asked to rank them in terms of their final angular speed. So they start from rest and we need to work out their angular speed. In order to work out their angular speed, we will also need to use the angular momentum, but we will use that the angular momentum is equal to I omega. So the angular momentum is going to depend on the moment of inertia. Now each of these is rotating about an axis through the middle of the shape, so this axis here. So we need to work out how big the moments of inertia are relative to each other. So they've all got the same mass. The one with the smallest moment of inertia is going to be the one which has the most mass closest to the center. So that's going to be the sphere. As it has more mass, it's wider at its center than it is at the edge. So we've got that the moment of inertia of the sphere is less than the moment of inertia of the disc. And then the hoop's got the largest because all the mass on the hoop is concentrated near the outer edge. Okay, so if we've got a big moment of inertia, we will have a small angular speed in order to have the same angular momentum. So in this case, we're going to have that the speed of the angular speed of the sphere is greater than the angular speed of the disc, which is greater than the angular speed of the hoop.
Now, as in the translational case, we also have a law of conservation of angular momentum. This tells us that when there is no net external torque acting on a system, then its angular momentum is conserved. So with that in mind, let's try a little predict, observe, explain activity. In a minute, I'm going to sit on this chair and start it rotating. I've got two fairly heavy masses here. Initially, I'm going to hold them out like this, and then I'm going to bring my arms in like this so that the masses are closer to my body. So I want you to predict what will happen as I bring the masses in closer to my body. Okay, so let's try this now. You should now write down an explanation of what you just saw. Okay, so my explanation of what's going on. This is an example of conservation of momentum. Conservation of momentum tells us that the initial moment of inertia times the initial angular speed has to be equal to the final moment of inertia times the final angular speed, or II omega I is equal to IF omega F. Now when I had my arms out, I had a large moment of inertia as the mass was quite a long way from the axis about which my body was rotating. When I bring my arms in, there's more mass closer to the axis, so the moment of inertia is smaller. So in order for this equation to be balanced, when I have a big I need to have a small omega, so a lower angular speed. And when I have a small I need to have a much larger omega, so angular speed. So this is why when I brought my arms in, I sped up and started going much faster.
So this problem, consider a plane inclined at an angle of theta degrees above the horizontal with a massless inextensible chord joining M1 and M2 passing over a pulley with radius r and mass m as shown in the figure below. Assume that M1 is sliding up the plane with the coefficient of kinetic friction between the plane being mu k. The tension to the left of the pulley is T1, while the tension to the right of the pulley is T2. Part A, write down an expression for the net force on M1. Part B, write down an expression for the net force on M2. Part C, write down an expression to describe the net torque on the pulley. Part D, use these expressions to come up with an expression for the acceleration of the system. And then Part E, how would this expression change if it was sliding down the inclined plane? Okay, so in this problem we've got an inclined plane, inclined at an angle theta, and we've got M1 on that plane, and we've got this pulley here and M2 hanging down here. And in part A, we're asked to write down an expression for the net force acting on M1. So we know that the net force is given by M1A. And in this case, we're told that M1 is moving up the slope. So the force pulling it up the slope is the tension in this string. So we've got the tension in the string. Now let's consider the other forces acting on our mass M1. We've got the weight force going down, so that's the mg, and we can split this weight force into components. So we've got the m1g sine theta pulling it down the slope, and then our normal force is going to be equal to m1g cos theta. So we've got the weight force pushing it down into the slope, and that causes this normal reaction force here. So we've got m1g sine theta pulling it down the slope, and then this reaction force results in the friction, so we've got minus mu k m1g cos theta, which is also pulling it down the slope, opposing its motion up the slope. Okay, so that's our answer to part A. For part B, we're asked to write a similar expression for mass 2. So with mass 2 over here, we've got M2G, which is pulling it down, its weight force, and then we've got our tension force, T2, pulling it up. So those are the only forces acting on this second mass. So it's a bit simpler. We can write M2A is equal to M2G, which is causing it to accelerate down, and then minus T2, which is pulling it up. Okay, now part C, we're now needing to write an equation for the net torque on our pulley here. So it's a disc with radius R and mass capital M. And so we've got the tension here. So this tension T2 is pulling it around this way, and tension T1 is pulling it around that way. So because it's moving this way, we know that T2 is bigger. So the net torque, we've got T2, which is acting at radius R, and then in the opposite direction, we've got T1, which is also acting at radius R. And we know from Newton's second law for rotation that this is going to be equal to I alpha. So we've written down an expression to describe the net torque there. Now in part D, it asks us to combine these expressions to come up with acceleration. So the first two are fine, they've got acceleration, but we're going to need to work on this third one a little bit in order to get our acceleration. So we know that the moment of inertia of a disk is given by a half mr squared, and the alpha is related to the acceleration through a over r. So we can substitute these two expressions in here. So we've got the I, which is a half. So we've got I, which is a half mr squared times a on r is equal to, let's take r out as a common factor, r t2 minus t1. Now we can cancel some r's. We've got an r squared here, which we can cancel with that r, and then we've got an r on both sides, which cancel each other out. So we end up with a half ma is equal to t2 minus t1. And now we've got three equations, 1, 2, 3, which we can solve simultaneously in order to come up with our expression for A. So let's do 1 plus 2 plus 3. This tells us that M1A plus M2A plus a half MA is equal to T1 minus M1G sine theta minus mu K M1G cos theta plus M2G minus T2 plus T2 minus T1. So these tensions all cancel out, and we can pull the acceleration out as a common factor. So we have A times M1 plus M2 plus a half M is equal to M2G minus M1G sine theta minus mu K M1G cos theta. And so then we can rearrange this, and we have A is equal to M2G minus M1G sine theta minus mu K M1G cos theta, all divided by M1 plus M2 plus a half M. So we've now come up with our expression for acceleration. So if we were given numbers, we could substitute them in. Now in part E, it asks us how would this expression change if M1 was sliding down the inclined plane. Okay, so M1's now going down the plane, so everything's going this way. What's a bit different is that the friction force is then acting up the plane. So if we wanted to rewrite these expressions, we'd have M1A is equal to M1G sine theta's now the biggest force, which is pulling it down, but the friction is opposing this, so this is minus mu K M1G cos theta, and then the tension force is pulling it up. M2A, we've now got it's being pulled up, so T2 minus M2G, and our moment of inertia is also in the opposite direction, as now T1's bigger than T2. So we've got a half ma is equal to T1 minus T2. Then once again, we can sum all these together. So hopefully you can see we'll end up with A times M1 plus M2 plus a half capital M. And these will cancel, the T's will cancel, and we'll end up with M1G sine theta minus mu K M1G cos theta minus M2G. And so to get the acceleration, we just need to divide by this. So this will be over M1 plus M2 plus a half M, and we get rid of that from there because I divided by it instead. I just didn't want to write it all out again. So this is our new expression. So we may have expected that it would just be the negative of this acceleration as the acceleration has changed direction. But because the friction also changed the direction that it was acting, in the first case it was opposing the motion, so it was pulling it back down the slope. In the second case, it's still opposing the motion, but now to oppose the motion, it's pulling it up the slope. It's not quite the negative of this expression. We needed to flip the sign in front of the friction. So our question is, a disk of mass m, 2.0 kilograms, and radius r equals 0.10 meters starts from rest. A hanging mass, m is equal to 1.0 kilograms, is released at t equals 0 seconds. Part A, what is the acceleration of the hanging mass? Part B, what is the angular speed of the disk 2.0 seconds after the mass is released? C, what is the kinetic energy of the disk at this time? D, how much work has been done on the disk? E, what is the kinetic energy of the hanging mass? F, has mechanical energy been conserved? Okay, so to answer part A, we should consider the forces which are acting on the hanging mass. So we've got our weight force, which is pulling it downwards, and then there'll be a tension force in the string, which is pulling it up. So we can use Newton's second law to write ma is equal to the weight force, mg, minus the tension. Now we can also consider the forces which are acting on our disk here. So we can use Newton's second law for rotation to write down an equation for the disk. So we know that the moment of inertia of the disk times the angular acceleration of the disk is equal to the torques acting on the disk, and in this case the torque is caused by the tension force which is acting at radius r, so this is equal to RT. Now because it's a disk, we know that I is equal to a half mr squared, and alpha is related to our acceleration through alpha is equal to a over r. So we can simplify off some of the r's in this case. This r will cancel this r, and we've now got the equation RT is equal to a half mRA, and so because there's an r on both sides, those will cancel each other out, and we end up with the tension is equal to a half ma. So we can then replace this expression for tension here with the one that we've calculated from over here. So we've got this is equal to mg minus a half ma. We're trying to find this acceleration. So if we move all our acceleration terms onto one side, then we've got ma plus a half, this is a capital Ma, it's the mass of the disk, is equal to mg. And so that tells us that pulling the acceleration out as a common factor and then dividing by what's left, we can write this as acceleration is equal to mg over m plus a half. This is capital M. So this is now something that we can evaluate, as in the question we've been given all of these. So the mass of the hanging mass was 1 kilogram, so we've got 1 times 9.8 over 1 plus a half times the mass of the disc, which was 2 kilograms. So we're doing 9.8 divided by 1 plus 1, which is 2. So this gives us 4.9 meters per second as the acceleration of the hanging mass. Now in part B, we're asked what is the angular speed of the disc 2 seconds after the mass is released. So in order to do this one, we'll need to consider our rotational kinematic equations. So just as we have v equals u plus at in the translational case, we have omega is equal to omega naught plus alpha t in the rotational case. Now we know that this disk starts from rest. So omega naught, the initial angular speed, is 0. So we can solve for alpha because we know that alpha and a are related through alpha is equal to a over r. So this is equal to a over r times t, and we have just calculated a here. The acceleration of the hanging mass is the same as the tangential acceleration of the disk here. So this is 4.9 times 2 over 0.10, and so that is equal to 98 radians per second is the angular speed of the disk at the end of the 2 seconds. Now part C says what is the kinetic energy of the disk at this time. So we can calculate the kinetic energy using this is equal to a half I omega squared. So this is a half. Now because it's a disk, the moment of inertia is a half mr squared, and then omega squared we've just calculated. This is 98 squared. So we've got a half times a half, so that's a quarter, times the mass of the disk, which is 2 kilograms, times the radius squared, so that's 0.10 squared, times 98 squared. And solving this, we end up with 48 joules. Now part D says how much work has been done on the disk. Now we could just go back to the work kinetic energy theorem and say, well, if this is its change in kinetic energy, this is the amount of work, but that's cheating a little bit. Let's calculate it using our work is equal to the integral of the torque d theta. And the limits here are from theta initial to theta final. Okay, so theta initial we'll take as 0, and then we need to calculate the total angle through which it's moved in order to get our theta final. So in order to do that, we can use our equivalent equation to S equals ut plus a half at squared, which tells us that theta is equal to omega naught t plus a half alpha t squared. Omega naught, we've said the initial angular speed 0, so that's 0. So this is equal to a half times a over r, so that is a is 4.9 over r, which is 0.10, times t squared, which is 2 squared. Solving this, we end up with 98 radians. So that's our final angle here. We also need to calculate the torque. So the torque is equal to the radius times the tension force. We don't have a value for our tension force at present, so we're going to have to get one. We can get one by looking at this equation here. So rearranging that equation to make tension the subject, we end up with tension is equal to mg minus ma. And so this is equal to mg minus a. This m is the hanging mass. So this is 1.0 times 9.8 minus a, which we calculated in the first part as 4.9. So this is equal to 4.9 newtons. So now we have the radius and we have the tension. So our torque is equal to 0.10 times 4.9, which is equal to 0.49 Newton meters. And this is a constant value. So we can now put this into our integral equation here. So our work done, we're going from 0 up to 98 radians, and our torque is 0.49 times d theta. Doing this integral, we end up with 0.49 theta, and that's from 0 to 98. And so this is equal to 0.49 times 98. When we substitute in the 0, this term disappears, so we don't need to subtract that off. Solving this, we end up with 48 joules. So that can make us happy because the change in kinetic energy was 48 joules, and now we've calculated the work done on this disk, and that's also 48 joules, and we were expecting these two to be the same, and they are. Okay, so part E now asks us, what is the kinetic energy of the hanging mass? So we know that the kinetic energy is equal to a half mv squared. So we've calculated the acceleration of the hanging mass in the first part. So we can use our kinematic equations to work out what v is. We can use v is equal to u plus at. It starts from rest. The acceleration is equal to 4.9. The time is 2 seconds, and so this is equal to 9.8. So our kinetic energy is equal to a half times the 1 kilogram times 9.8 squared, and solving this, we end up with 48 joules. So let's just put that in the box there. And now part F, just making some space here. Has mechanical energy been conserved? So in this process, the hanging mass is losing potential energy, and that's being converted to kinetic energy of both the disk and the mass. So we'll need to calculate how much potential energy this hanging mass has lost. So we'll need to calculate mgh, and to do that we'll need to know what height it's fallen through. So in order to calculate h, we can use our kinematic equation. S is equal to ut plus a half at squared. It starts from rest, so u is 0, and so this is equal to a half times 4.9 times 2 squared. Solving this, we end up with 9.8, and so our potential energy is equal to 1 kilogram times 9.8 for g times 9.8 for the height, and solving for that, we end up with 96 joules. So this is the potential energy that it's lost, and that has gone into the kinetic energy of the disk plus the kinetic energy of the hanging mass plus the kinetic energy of the disk. So you can see 96 is equal to 48 plus 48. So this tells us that mechanical energy has been conserved. So in this problem, a cylinder with a length of 10 centimeters, a radius of 5 centimeters, and a mass of 2 kilograms rolls down a plane inclined at 30 degrees to the horizontal. It starts from rest and travels a distance of 1.2 meters along the plane. The moment of inertia of the cylinder is given by I is equal to half mr squared. Part A, what is the change in gravitational potential energy as the cylinder rolls down the plane? Give your answer as positive if it increases, or negative if it decreases. Part B, what fraction of the final kinetic energy is in the form of rotational kinetic energy? Part C, what is the speed of the cylinder at the bottom of the plane? Part D, what was the acceleration of the cylinder as it rolled down the plane? And E, what is the size of the frictional force acting on the cylinder? Okay, so in this problem, we've got an inclined plane, which is inclined at an angle of 30 degrees, and we've got a cylinder which has a length of 10 centimeters. It actually turns out that we don't need that length, and a radius of 5 centimeters. At the top of it, it has a mass of 2 kilograms. And it then rolls down the plane. It rolls here a distance of 1.2 meters. And we're asked in part A, what is the change in gravitational potential energy of the cylinder as it rolls down the plane? So the change in the gravitational potential energy is going to be equal to mgh final minus mgh initial, and the final height's lower than the initial height, and we can work out by how much. This is our delta H here, and by looking at the trigonometry we can see that sine 30 is equal to the opposite, which is delta H over the hypotenuse 1.2. So that tells us that delta H is equal to 1.2 times sine 30. So we can write this as mg times h final minus h initial, which is mg delta h, which we've got here. So this is equal to m, which we said was 2 kilograms, times g, which is 9.8, times the change in height, which is 1.2 times sine 30. And solving that on the calculator, we get 11.76 joules. So that is equal to 12 joules to 2 significant figures. Part B then asks us what fraction of the final kinetic energy is in the form of rotational kinetic energy. Okay, so at the bottom of the slope here, we have rotational and translational kinetic energy. So the rotational kinetic energy is given by a half I omega squared. We're told that because this is a cylinder, I is equal to a half mr squared. And we know that omega and v are related through v is equal to omega r, which tells us that omega is equal to v over r. So we can write this as a half times a half mr squared times omega squared, which is v squared on r squared. So now you can see our r's are cancelling out, and we've got a half times a half, which is a quarter mv squared. So that's the rotational kinetic energy. The translational is given by a half mv squared. So you can see that a half mv squared is double a quarter mv squared. So this is equal to 2 times k rotational. So given that our translational is double our rotational, we have 1/3 going into rotational and 2/3 going into translational. So 1/3 of the kinetic energy and 2/3 is translational. Okay, part C then asks us what is the speed of the cylinder at the bottom of the plane. Okay, so at the bottom it's lost all this potential energy and it's lost it into the rotational and translational kinetic energy. So we've got U initial is equal to K rotational plus K translational. And up the top we worked out what UI was. It was 11.76. We'll keep all our significant figures for our working here. And K rotational, that's equal to a quarter mv squared. K translational, that's equal to a half mv squared. So we've got a quarter plus a half. So this is 1/4 plus 2/4. So that's 3/4 mv squared. Okay, now we're trying to solve it for v. So we can rearrange this and say, well, v squared is equal to 4/3 times 11.76, and then we're dividing by this mass. So the mass is equal to 2, and so this is equal to 7.84. That's the v squared. So this tells us that the speed is equal to 2.8 meters per second. And again, we've given it to 2 significant figures. In part D, we're then asked to find the acceleration of the cylinder. So we know its final velocity and we know how far it's traveled. It also is going to undergo constant acceleration because it's got constant forces acting on it. We've got the frictional force and the weight force. So those forces aren't changing. So the acceleration should not change. So because the acceleration is constant, we can use our kinematic equations. And one of those is v squared equals u squared plus 2as. In this case, the initial speed is 0. So we've got v squared is equal to 2as. And so rearranging this for a, we have a is equal to v squared over 2s. So that is equal to 2.8 squared over 2. Now s, that's the displacement down the slope. So that's times 1.2. And so this is equal to 3.27 meters per second. So that's equal to 3.3 meters per second. Now, part E then asks, what is the size of the frictional force acting on the cylinder? Okay, so let's imagine the cylinder at this point. Now, the forces acting on it, we've got the weight force pulling it down. So that has got a component down the slope. This is mg sine theta. We also have the frictional force, which is pushing it up the slope. So with Newton's second law, we can write, well, ma is equal to the sum of the forces acting on it. So we've got mg sine theta down the slope minus the frictional force up the slope. So rearranging it, because we're trying to find the frictional force, we've got the frictional force is equal to mg sine theta minus ma. And now we can just substitute in. We've got 2.0 times 9.8 times sine 30 minus 2.0 times a, which was 3.27. And solving that, we end up with 3.26, which is 3.3 newtons. So that was one way to do it. There is actually another way to do it as well by considering the torque. So if we imagine the cylinder on the slope, we've got the frictional force pushing it up this way, and that is producing a torque at radius r. So what we can do is we can use Newton's second law for rotation, which tells us that the torque, the sum of the torques, in this case there's only the one torque caused by this force here, is equal to I alpha. So the torque is equal to the force times the cross product of the frictional force with the radius. They're at 90 degrees to each other. So this is just equal to the frictional force times the radius. And I, for a cylinder, we said was equal to a half mr squared. And then alpha is related to the acceleration, as alpha is equal to a over r. So we can rearrange this. We've got our frictional force is equal to a half. Now, mr squared, and we've got an r on the bottom here, and this r will come down the bottom too. So we've got two r's on the top and two r's down the bottom, so they'll cancel out. So we've still got the m and we've got the a. So the frictional force is equal to a half ma, which allows us to calculate it now. So we've got a half times 2 times a, which was 3.27. So that's just 3.27, which we can write as 3.3 newtons. So these two methods gave exactly the same answer, which is good. So that was a way to check that our answer was actually correct. And another problem. A 0.5 kilogram block is attached to the end of a rod with a length of 0.6 meters. The rod is not of uniform density. It has a mass of 0.5 kilograms and a moment of inertia of 0.060 kilogram meter squared about the axis through A. Assume that the block can be treated as a point particle. A bullet with a mass of 1 gram is fired at the block. The bullet embeds itself in the block. When the bullet has embedded in the block, what is the moment of inertia of the block bullet rod system? And part B, if the angular speed of the system just after the bullet had embedded in the block about A is 4.5 radians per second, what is the speed of the bullet just before it enters the block? So in this question, we've got a rod. It's got a length of 0.60 meters, and it's got a mass of 0.50 kilograms, and we're even given its moment of inertia. Its moment of inertia is 0.060 kilograms meters squared. And then on the end of the rod is a block that we're told we can treat as a point mass. So the mass of the block is equal to 0.50 kilograms. And heading towards that block, we've got a bullet here, and the speed of the bullet is unknown, but the mass of the bullet is equal to 1 gram. Now, in the first part of the question, we're asked to calculate the moment of inertia of the system once the bullet has embedded in the block. So let's draw a little diagram down here. We've got our block here with our bullet embedded in it, and we're finding the moment of inertia about this point. Now, the nice thing about moments of inertia is that they just add together. So the moment of inertia of the system is going to be equal to the moment of inertia of the rod, which we're told, the moment of inertia of the block, plus the moment of inertia of the bullet. So the rod we're actually given, so this is 0.060. Now we're told that we can treat the block as a point mass, and we know that the moment of inertia of a mass is given by mr squared. So this is just equal to the mass of the block times, now it's a point mass, a distance L from the pivot point A. So this is times L squared. And then for the bullet, because the block's treated as a point mass, we can assume that the bullet which is embedded in it is also a point mass, which is also a distance L from this pivot point. So that's plus the mass of the bullet times L squared. Now the mass of the bullet is so much less than the mass of the block that if you wanted to ignore it, you could. It wouldn't actually make a difference to the final answer, but let's include it anyway. Okay, so we've got 0.060 plus the mass of the block, that's 0.50 times 0.60, that's the length squared, plus the mass of the bullet is 1 times 10 to the minus 3 kilograms, because it's only 1 gram, plus 0.60 squared. And solving this on the calculator, we get 0.24036, but we only want to give it to two significant figures. So this is 0.24, and that is kilograms meters squared. Now in part B, we're asked to find the speed of the bullet. So this is what we're trying to find. And we're told that the final angular speed of the entire system is given by 4.5 radians per second. So in order to do this, we're going to make use of our law of conservation of angular momentum. So we know that the initial moment of inertia times the initial angular speed will be equal to the final moment of inertia times the final angular speed. Now we're given the final angular speed and we have just calculated the final angular momentum. So we know both of these. So what we need to do is work out these things. Okay, so let's draw a little diagram to show the moment that we're considering. So we are considering the moment just as the bullet is about to enter the block. So the bullet is moving, but the rod and the block are stationary. So we know that omega initial of the rod is equal to 0 because it's stationary, and the initial speed of the block is equal to 0 because it's stationary. Now, as the bullet enters the block, it's going to cause it to rotate around this way. So the speed of the bullet is related to its angular speed through our equation V is equal to omega r. And so the initial angular speed of the bullet is given by its initial speed over the length of the rod, because that's the distance from the pivot point at which it enters the block. So we'll be substituting that in to find our V0. So it's only the moment of inertia of this bullet about this pivot point which is going to count. So the moment of inertia, it's a point particle again. So we're just going to once again use this equation up here, but in this case the mass is going to be the mass of our bullet. So we have that the I initial of the bullet is equal to the mass of the bullet times L squared. And so just substituting everything in here, we've got that the mass of the bullet times L squared, that's the I initial, times omega initial, which is V naught on L, is going to be equal to 0.24 times 4.5. Okay, and we're trying to solve this for V, so one of these L's cancels out, and we can rearrange this to write, well, V naught is equal to 0.24 times 4.5, and now we'll need to divide by the mass of the bullet, which is 1 gram, so 1 times 10 to the minus 3, and then we'll also need to divide by the length, which is 0.60. And solving that, we end up with 1,800 meters per second as the speed of the bullet.